Chapter 4, Ohm's Law, Power and Energy. Today we're going to be looking at Ohm's Law. Ohm's Law is the fundamental relationship in electricity that describes the relationship between voltage, current, and resistance. And whether you're a technician, an engineer, an electrician, or even an automotive mechanic, you're most likely using Ohm's Law on a daily basis and without even realizing it. But it speaks to what an important relationship it is to understand when it comes to working with electricity. It's one thing just to be able to look up the relationship on a formula sheet or to find numbers in a question and know how to use them to come up with the unknown value. But it's another thing to really understand the relationship that's going to further help you when you're doing labs, when you're troubleshooting, when you're designing a circuit or working with electricity. So if we look at the most important thing we can take away from this semester 1 course on electricity, it would probably be summarized by Ohm's Law, because it's through Ohm's Law that we can use that relationship to understand all the other relationships, like for power and energy. Okay. So if we go back to the water analogy that we looked at from chapter 2, remember in this case we've got a pump that's providing essentially our charge separation or our difference in pressure to motivate flow, to move water through this system. Without the pump, without the charge separation or the pressure difference of low and high on either side, we would have no potential to do work. But with it, we have flow, and you can see here we've included the restriction. So that would be a kink or a bend in that conductor or a kink or a bend in that pipe. And when the flow entered that restriction, there would be work being done. This is okay. So if we look at the relationship here now, remember it's the pump that's providing our pressure to motivate flow. And if we were look at keeping if we would look at the effect on flow as let's call flow the dependent variable here. If we were to look at keeping the restriction the same, or the resistance in this circuit the same, and we were to increase the pressure, what would be the result on flow? So let's go here and say if we were to increase the pressure and keep the restriction the same, what would be the result on flow? Higher pressure means you're going to have more flow. There's a direct relationship between the pressure and the flow. Increased pressure, flow goes up. Decreased pressure, flow goes down. What happens if you maintain the same pressure? So now I'm going to say that pressure is the same. And we increase the restriction. So that means we kink this even more. What happens if we make the restriction or the resistance go up? When the resistance goes up, we will notice that we have less flow. The flow will go down. Notice how there you have an inverse relationship between the restriction or the resistance and the flow. That's assuming keeping the pressure the same. So if we just look at that to describe Ohm's law, we can say that pressure is equal to voltage in our circuit. Flow is equal to current. And restriction is equal to resistance. That being said, we could make a relationship involving the symbols of V, of I, and R. And let's put it in terms of our dependent variable, current. The current is dependent on both voltage and resistance. So in terms of the dependent variable I, we could say the flow, I, is directly related to the voltage. Directly related. Remember, when voltage or pressure went up, flow or current went up. So that means we've got a direct relationship between I and V. let's go back to our relationship for resistance and flow. When resistance went up, flow went down. Likewise then, you would say if resistance went down, flow would go up. We have an inverse relationship. That means we can write the relationship such as this: I equals V over R. So here we see an example of a pictorial or wiring diagram showing a battery or a DC source. In this case, it's a battery. We can see this is the positive terminal, this is the negative terminal. Conventional current flow would have current in this direction. We can see that if we look here, we can see a resistance. This provides our restriction, like the kink or the bend in that conductor or that pipe. This is where the flow is going to do work, and there'll be power dissipated by that resistor in the form of heat. So it's flow through that restriction that's going to result in work. If we look here, we can see this is clearly an ammeter to measure current, right? And how do we know it's an ammeter to measure current? Well, first of all, we have the quantity representing current here, but second of all, its connection is a series connection. This circuit had to be broken, opened, so that we could enter the ammeter in series, just like it was another load in the circuit. Just like it was a resistive load, we had to add the ammeter in series. Over here, we can see this is representing our voltage, or our pressure, if you want to think of it that way. And we had an across connection, or we had a parallel connection, with one side being on the negative terminal of the battery and the positive lead being on the positive terminal of the battery. And therefore, in this case, we're reading 12 volts. So we can look at this as the as values that can be calculated based on Ohm's law. What don't we know here? We don't know what value the resistance is. So through the use of Ohm's law, we could determine the value of R here. Now, what's our unit for R? Ohms. So what does it mean for R? R will be a value of V divided by I. If we take the value of V equaling I times R, or I equaling V over R, and R equaling V over I, we can use these quantities to determine our value of resistance. What we need to understand is that 1 volt divided by 1 amp will equal 1 ohm. So we can go through a process to determine the amount of resistance in this circuit by simply going R equals V over I. We have 12 whole units of volts divided by 100 times 10 to the minus 3 amps. And now you could come up with a calculation of the resistance, right? So it would be one way to handle these problems is to directly input the power of 10 in your calculator before you process this, and then so if you took a moment to put that in your calculator, if you had your calculator in engineering mode, you would go 12 divided by 100 exponent minus 3, and then you would come up with a result of 120 ohms. 120 whole units of ohms would be the answer you would get for this simple example. So Ohm's law says the current in a resistive circuit is directly proportional to the applied voltage and inversely proportional to its resistance. Therefore, I equals E equaling V, so E equals V divided by R. For a fixed resistance, doubling the voltage doubles the current. Okay, for a fixed resistance, that means the resistance hasn't changed. Doubling the voltage will double the current. For a fixed voltage, doubling the resistance will halve the current. That means it'll be 1/2 or 50% of what it was. Ohm's law may also be expressed in terms of E or R. So E is equal to I times R, or just like we saw in the previous example, R is equal to E or V over I. So when we're doing these problems, it says express all quantities in base units of volts, ohms, or amps, or utilize the relationship between prefixes. So when we say the relationship between prefixes, we mean something like whole units divided by milli-units would give you kilo units. Likewise, whole units divided by kilo units is going to give you milli-units. And that's, of course, the relationship between prefixes. So whole units is 10 to the 0. Milli-units is 10 to the minus 3. The result is going to be, when you take and divide your powers of 10, the result is going to be a subtraction. So that's going to be minus 3 turns into a plus 3, and you have your kilo units. When you look at here, 10 to the 0, 10 to the plus 3. Remember, you subtract when you exponents when you divide, so the result here is going to be 10 to the minus 3, of which you know is milliunits. So that's what it's talking about when it says the relationship between prefixes. We're talking about engineering prefixes: milli, micro, kilo, mega. Okay, let's take a look at these examples, and we'll just work through them one at a time systematically to get the idea. If we look at the first group here vertically, we can see that in each case the resistance is the same. Notice how our resistance of 10 ohms is the same in each case. Let's look at our voltage. Our applied voltage is being doubled, then tripled, right? So we have 10 volts first, 20 volts in the second example, 30 in the last. Notice how in the first one we have calculated a value of 10 divided by 10, so 10 whole units of volts divided by 10 whole units of ohms gives us 1 whole unit amp. In the second example, we've doubled the applied voltage, so now our pressure is doubled. Our pressure has doubled to the same restriction, or the same resistance. That means our flow would have to double. There's that direct relationship. So now look at the flow doubling, and then I think you get the idea down here. The flow has tripled from what it originally was because we kept the resistance the same, and tripled the applied voltage. If we look back to here, that's triple the applied voltage. Now we look at working with the opposition, or the resistance, in this second example, and notice how the applied voltage as E is the same value for all three. We start with 12 ohms and calculate 3 amps of flow. We double now that resistance, so we have 24 ohms. We have an inverse relationship between voltage and between resistance and current. So if we double the resistance, we know we're going to have the current, right? So now we have a current 50% of what it was. And now we move on to the last example where we tripled the opposition. We're going to have a value 1/3 of where we started. So we can see that our 1 amp is 1/3 of where we started, based on the fact we tripled our opposition, or tripled our resistance. Okay, so let's give this a try then. A 27 ohm resistor is connected to a 12 volt battery. What is the resulting current? So this is one of our first questions we've been given as a word problem. And our job is to follow all the steps that we would follow as our blueprint, if you will, for problem solving, that as problems get more difficult, more involved, we've practiced the steps for simple problems that we're going to apply to more difficult problems. What's the first thing we're going to do? We're going to draw a diagram. And that diagram makes the most sense to make it a schematic diagram with the source on the left and the load on the right. That's common in all systems and circuits, is to have the input or the input energy on the left and have the output energy or flow on the right. Label the known values. What do we know here? We'll come back to that. 27 ohms, 12 volts. So label the known values. So in this case, 27 ohms and 12 volts is what we'd add to our diagram. Now it says determine which value is to be calculated. It's wanting to know what's the resulting current, right? So here's where we're going to say I is what we need to determine. And then lastly, we use relationships and laws to solve. Okay, so what would that look like in terms of a diagram? Okay, so remember, our first job is to draw the diagram. Notice how I'm going to put my source voltage on the left. I'm going to show my resistance as my load on the right. I'll label this V. I'll label this R. And we've been clearly given the values of V and R. So I'll say V is equal to 12 volts. R is equal to 27 ohms. And their next step is to determine what quantity it is we're to determine. And in this case, we know it's current. So I in this circuit is what we need to figure out, right? So now we can use relationships and laws to solve. So I equals 12 volts divided by 27 ohms. So that's whole units of volts divided by whole units of ohms. So that's 12 divided by 27 to give us 444 with the exponent minus 3. And we know the engineering prefix for minus 3 is milli, so that would be milliamps. 444 milliamps. Okay, so let's try this one. A lamp draws 25 milliamps when connected to a 6-volt battery. What is its resistance? First job, draw a diagram. 6 volts. Lamp, L1. The L1 resistance, we don't know. The current, I, is equal to 25 milliamps. So now we'll use the relationship of prefixes. So we know that R equals V over I. We have V equal to 6 volts. We have I equal to 25 milliamps. We know that that's equal to 6 volts over 25 times 10 to the minus 3 amps. We know if we take our 6 volts and divide it by 25, our result is going to be in kilo amps, right? So let's try that. 6 divided by 25, the result is 240 to the minus 3 kiloamps, which we know as a result is going to be 240 ohms. Okay. So if we look here, you guys can solve for the values. And notice how these are diagrams of which were not drawn with our standards for sources on the left and loads on the right. And that's done purposely in order for you to be able to identify or find the sources of voltage and add them all together. In this case, there's only one. And all your loads and add them all together. And in this case, there's only one load and one source to deal with. So we're looking for current in each one of these examples. And how would you find it? In this case, I would equal 65 volts divided by 22 times 10 to the 6th ohms. I here would equal 18 volts divided by 6.8 times 10 to the 3rd ohms. And how about here? I would equal 140 volts divided by 330 ohms, or whole units of ohms. Okay, when we look at the linear relationship of voltage and current and resistance, we can see that's being shown here in this diagram. And it means that for any value of voltage or applied voltage, we can determine the current by looking at the graph. So these are volts on the bottom, these are amps here. If I look at 20 volts, that's going to result in 2 amps when my resistance is 10 ohms. That same 20 volts, when my resistance is 20 ohms, is going to result in 1 amp. Right? So if we look at that example there, we can tell clearly that we have less resistance when we have more current. So let's say I was to just remove this, and I was to say, what is the value of R for this one, and what is the value for R for this one? Based on the linear relationship, you could take any value of voltage, like say 40 volts, divide it by the value of current, in this case 4 amps. 40 divided by 4 would give you R equals 10 ohms. And you could calculate the value of opposition or resistance using Ohm's law. Okay, so now we're talking about shorts and opens, and this is related to something we talked about when we looked at a switch. We used a switch to demonstrate a short and an open. When a switch is in its off state and prevents current flow and doesn't allow current to flow to the work producing load, we call the switch an open circuit, and that's why we say the switch is open or off. When we look at a switch that is closed, it's corresponding to a short circuit. It allows maximum current flow, and it delivers or enables the load by allowing flow to do work at the load. So current can only exist when there is a conductive path, or a path for current to flow. When there is no conductive path, we refer to that as an open, or an open circuit. If I equals 0, then Ohm's law gives us a resistance value of E divided by I, or E divided by 0, which equals infinity. So that's where we say an open circuit has infinite resistance. And that's what we said when we looked in the value on an ohm meter in the lab of an open switch, or a switch that was in the off state. We read OL on the meter, of which we said was infinite resistance. Okay, so in this case, with a missing load here, this is an open circuit. In the last lab, when you guys removed the lamp from the lamp holder in that circuit, you created an open circuit. There's no longer a load, and you had 2 terminals, 2 load terminals like A and B here, in which you had an open circuit, and the resulting current was no current flow and infinite resistance. Okay, so this is a rule for voltage that you'll see violated all the time, but in truth, voltage sources in a DC circuit should carry uppercase E. Low voltages, as in lamps, resistors, heaters, motors, should carry the symbol V for voltage. So that means that if you were to label the voltage of a lamp, you would call it V. The voltage of a source, you would call it E. Again, you'll see this is violated in all sorts of labs, curriculum, textbooks, and so on. But that is really the use of this E and V that we've talked about. So if we look, since V equals I times R, these voltages are sometimes referred to as IR drops. So when you have resistors in a circuit, so that means if we have, just as an example, a resistance here in a circuit, the voltage that we would calculate as I times R when it comes to this circuit is sometimes just referred to from the resistance as an IR drop or a voltage drop. So when it comes to voltage drop polarities, what we need to understand is the polarity that's developed by the current flowing through a resistance or a restriction is determined by the direction of current. So it'll be the direction of current through a load that determines the voltage drop polarity. And just like we've talked about in terms of conventional current, the current enters the positive potential of the drop and exits the negative. So notice how in each one of these cases, I is entering the positive terminal and exiting the negative terminal. Entering the positive terminal, exiting the negative terminal. It's the flow that determines the amount of voltage and its polarity. So the direction of current determines the voltage drop polarity, the amount and the resistance determines the magnitude of that voltage. So the polarity of voltages across resistors is of extreme importance in circuit analysis. Current enters the positive and exits the negative. Place the plus sign at the tail of the arrow and the negative sign at the head of the arrow. So in all cases, that's what we've done. We've used the direction of current in each one of these diagrams to determine the voltage drop polarity. Voltage drop polarity 1 with the current entering the plus, exiting the minus, entering the plus, exiting the minus. Determine the voltage drop and polarity of this example. It's going to be both the values of current and resistance to determine the magnitude. It's going to be the direction to determine the polarity. So let's start with, first of all, the polarity for the first one here. If we look at the direction of current, the polarity is going to result in plus, minus. Remember, entering plus, exiting the minus. Now, in terms of our magnitude, we just have to multiply those two values together. So that's whole units of amps is 0.1 times whole units of ohms would be 10 exponent 3 for kilo, and our answer would be in whole units of volts. In this case, the answer would be 1 volt. Okay, you look at the next one. What is our polarity? Entering the positive, exiting the negative. Multiply your whole units of amps as 0.15 exponent minus 3, being that it's milliamps, multiplied by 3 exponent 6, knowing that that's the power of 10 corresponding to engineering prefix mega. Multiply the two together and you get 450 volts, whole units of volts. Okay, let's look at these ones. Current enters the positive, exits the negative. You take 0.3 whole units of amps, multiply it by 400 whole units of ohms, and your answer is 120 whole units of volts. Okay, next one. Current enters the positive, exits the negative. Do your multiplication using whole units or engineering prefixes. In this case, it's 2.5 whole units of amps multiplied by 0.4 whole units of ohms to give you a result of 1 volt. Okay, so notice how here it says when it comes to current direction, we normally show current out of the plus terminal of a source. Remember, conventional current shows the current leaving the source, returning, or leaving the positive terminal of the source and returning to the negative. So our current, plus to minus, simply indicates the direction with respect to a reference. If the actual current in the circuit is opposite to that of a reference arrow, it'll be negative. If it's in the same direction as a reference arrow, it'll be positive. And remember, I talked about that before. Current has no polarity. It's the polarity given that indicates direction with respect to a reference. And in our case, because we use conventional current as our reference, if I was to show you an arrow for current that is opposite to that direction, we would express that as a minus. So let's take a look here. If we look at this direction of current, this is consistent with plus to minus current flow, and therefore the current has been expressed as a 5 amps. Look down here. The current is in the opposite direction to the direction of current as plus to minus, and therefore I has been expressed as minus 5. But it's the same circuit. It's just that because the reference arrow has been shown in the opposite direction to actual current, we've expressed it as minus 5. There's no difference in either of these circuits in the actual direction of current, the power is dissipated, or any calculations other than the current would be expressed as minus 5 because of the arrow shown opposite to that of our reference current, conventional current. Okay, here's where we look at power now. As far as power goes, power is work per unit time. So if we were to think of us, either you or I, doing the same amount of work, as in the same job, let's say it was cleaning up your house. If I can clean up your house in half the time that you can, I have twice the power. So it's work per unit time. And the more amount of work that's being done in that same amount of time, the greater the power dissipation. So when we think about, say, a lamp and a 100 watt lamp versus a 60 watt lamp, the 100 watt lamp is doing more work per unit time and producing more light energy for each second. And it would be the same with a heater. The greater the power rating of a heater, the more heat it's producing per second. A motor, the more horsepower it is, means the more mechanical work it's doing per second. So power is related to energy, which is the capacity to do work. So if we define power as the rate of doing work, power is equal to work per unit time. And if you remember, our unit for work is the joule, right? Our SI prefix, or sorry, our SI unit for time is the second. And when it comes to Q, that's our charge. So our Q, or charge, is the coulomb. So knowing what we know about voltage and current now, and we know now that power is defined as work divided by time, we can combine all these relationships to give us a new relationship to define power in terms of voltage and current. So if we look at power equaling work divided by time, and volts equal to work divided by charge, Therefore, work equals charge times voltage. We just transpose that relationship. If we look at current as our charge per unit time, or coulombs per second, that means P can equal QV divided by time, because QV is our work divided by time. Therefore, if we just move that formula around, we can say that P again equals V times QT. V being voltage and Q divided by T being I. Therefore, we can say that P otherwise is equal to V times I. So remember, V comes from this relationship, of which we came up with our relationship for work, which was QV. We divided that by time. We transposed this relationship to give us V times QT, which is equal to QV divided by T. And then we just identified this as I and identified this as V. That gives us V times I equals P. This is called Watts's law. Watt's law. P equals V times I. So what does that mean? Well, if we have P equals V times I, and we have Ohm's law for I equals V divided by R, we also have R equals V divided by I, and we have V equals IR, we can combine Ohm's law and P equals V times I to come up with all relationships of power for any two quantities. So let's say we wanted to define power in terms of V and R. What it means is we take P and we go V times I, expressed as V and R, to give us V times V over R, which equals to V squared R. Okay, what about if we wanted to express power in terms of I and R? P equals, now I've got to find the expression for V in I and R. We would say P equals I times R times I, because all we did was express V in terms of I and R. So that's going to be IR times I equaling I squared R. So now we've expressed P in terms of V and R, P in terms of I and R, and we already have P expressed as V and I. So the last thing it says here is power is always in the unit of watts, no matter which equation is used. As long as you're using whole units of volts and whole units of amps, you'll get whole units of watts. If we look down here, whole units of volts divided by whole units of ohms gives you watts. Here, of course, whole units of amps multiplied by whole units of ohms gives you whole units of watts. If you're not working with whole units, then you have to use the relationship between prefixes in order to get your result. So here, if we look here, we've got a 120 volt source voltage. Notice how the source voltage has been labeled with E. We have a voltage drop of 120 volts for this heater. You can see it's dissipating heat, and we have a resistance of 12 ohms. So we could determine P in any number of ways here. Based on the fact we don't have a value of I, we could just use our voltage and our resistance, and that would be P equals V squared over R. Our V value is 120 squared. That's our whole units of volts divided by our whole units of ohms to give us V squared divided by 12. That's going to be 1.2 kilowatts or 1200 watts. Okay, now what about if we look at another way of calculating this? We've got a value of 120 volts and 12 ohms. We can determine the current. So I equals V over R. Voltage is 120 volts. Resistance is 120 ohms, or 12 ohms. We can come up with a 10 amp value of current. We can determine P by I squared R, which would equal 10 squared times 12 ohms, which would equal 1.2 kilowatts once again, or 1200 watts. Okay, let's look at this next example here. Here we have voltage and resistance again. We can determine power directly by P equals V squared over R. So our V value is 10 squared over our R value of 20 ohms to give us 100 divided by 20, and the result being answers in watts, 5 watts. What about the next one? We have a value of 50 squared over 100 ohms to give you 25 watts. So we should also be able to use any of the power equations to solve for VIR if P is given. So we should be able to come up with any value of V, I, or R if we have P. So if we've got a problem that gives us power dissipation and a value of R, let's say, we could come up with a value of current where I equals the root of P divided by R. Or if we had a value of P and we're given value of voltage across a resistor, if we're given a value of P and a resistor, we could determine the voltage across it based on V equals the root of P times R. And where does this come from, of course? Well, P equals I squared R, so therefore I squared equals P divided by R, and I equals root P over R. Okay, get the idea. P equals V squared over R. So that means that we've got V squared equaling P times R, and V has got to equal root P times R. So one thing we have to be aware of when we're working with problems that involve power is there's two power values that we could see in a problem or in an example. One of them is the actual power being dissipated by the load, and the other one is its maximum power rating, meaning that it's a rating saying if you exceeded that power, you could damage it. So common power ratings are what's shown here. Let's say you had a 1/8 of a watt maximum power rating of a resistor. If you were to calculate that its power dissipation was more than 1/8 of a watt, you would expect it to be damaged. So it says a safety margin of 2 times the expected power is customary for design. So this is for design. So if you were to design a circuit that involved a resistor and you were to calculate the power dissipated, you would design the circuit such that you used a maximum power rating that's 2 times what you calculated. And this is essentially the safety margin. Okay? So energy is what you're billed for by your utility company, whether it's NMAX or ATCO or whoever it is. You're billed for energy. And even though they call it your power bill, it's actually your energy bill. And energy is determined by power times time. So if we think of 2 individuals owning a 1,000-watt heater, does that mean they're going to be billed the same every month because they both have a 1,000-watt heater? No. It's going to be determined by how long they run that 1,000-watt heater. So we have time involved here. So units for energy are watt seconds, watt hours, and most commonly, if you were to look at your energy bill, you're going to find a unit of kilowatt hours. So energy use is primarily measured in kilowatt hours by your utility company, and that's why when we do these cost of energy equations and any calculation of total energy, we use kilowatt hours. So we're going to convert our power values to kilowatts right away to make it simpler. So for multiple loads, the total energy is the sum of the energy of the individual loads. So let's say we wanted to figure out the total power of loads, and you had a 1,000-watt heater plus a 100-watt lamp plus a 60-watt lamp. Your total power would be 1,160 watts, and then it would simply be how long were you operating those loads all at the same time to determine what your energy consumed is. So it's power times time. So to figure out the cost then, it's quite simple. It's just your energy that you consumed as a kilowatt hour value multiplied by the cost per kilowatt hour. And when you have, in Alberta today, that's ranging from say 6 to 9 cents per kilowatt hour. And you would just multiply that value by the amount of energy you used. Now remember, we could turn this cost into an equation that involves power and time and cost, because we know that energy is equal to power times time. So we can just substitute that in there if we're working with power, time, and cost. And that's what we have in this next example. It says find the cost of running a 2,000-watt heater for 12 hours if the electric energy costs 8 cents per kilowatt hour. Notice how in the result here, where we figured it out, we changed right away 2,000 watts to 2 kilowatts. That allows us to be working with kilowatt hours, and that's what we have here, is a power times time, which is kilowatt hours. And when we have kilowatt hours, we can just simply multiply it by our cost per unit to come up with the result. So that would be 24 kilowatt hours multiplied by 0.08 to give you your cost of $1.92. So when it comes to systems where we have P in watts and P out in watts, what we need to understand is there's no power system, there's no mechanical system, there's no energy system at all in which it's at 100%. So we always have a P in value and a P out value, and P in is always greater than P out. And why is it always greater than P out? Because there's always losses. In physics, there's always losses and energy losses as a result of the work being done, and as a result, we have a value of P out that's less than P in. Or put otherwise, we can say that P in is equal to P out plus P losses. So energy can neither be created nor destroyed, but can be converted from one form to another. Electric energy into heat is an example. Mechanical energy into electric energy, such as an alternator. So this is what we have. So pore efficiency, because we're looking at efficiency now, and efficiency equals N. So pore efficiency in energy transfers results in wasted energy. When it comes to the heat that's being dissipated by that wasted energy, or the heat from the P losses, it says we can use fans and heat sinks to get rid of that. In order to determine N efficiency is always equal to P out over P in. And remember, P out is the smaller value. If we want to express efficiency as percentage, we can say N equals P out over P in times 100%. Likewise, we can say, if we're expressing it as work out divided by work in times 100% is going to give us a N in percentage, right? Now you can also express N as a fraction. It doesn't have to be expressed as a percentage. So that is, as an example, you could say 82% or 0.82. They're the same thing. Values of N can be expressed as percent or as a decimal fraction. Either one. So let's take a look at this. It says a 120 volt DC motor draws 12 amps and delivers 1.6 horsepower of power output. Okay, now what we're going to do is we're going to want to look at this in terms of all values of watts. And because it's asking what is the efficiency and what are the power losses. So we're going to have to do a conversion here, and we'll talk about that in a minute. But first of all, let's figure out what our P in value is. So we know we've got a DC motor, and that is a 120 volt DC motor, and the current through it is 12 amps. This is our P in value. So we can calculate our P in value. We can say P in equals V times I. And so we can say 120 volts multiplied by 12 amps gives you 1440 watts, or 1.44 kilowatts. Now, here's the thing. P out is equal to 1.6 horsepower. Okay, so with P out equaling to 1.6 horsepower, we need to convert horsepower to watts to make a fair comparison between P out and P in. So you'll learn this soon enough. 1 horsepower equals 746 watts. So now what we have to do to convert P out to watts is go P out equals 1.6 times 746. Okay, 1.6 times 746 equals 1194. So we have 1194 watts. Well, now, if we want to determine efficiency, we know efficiency N equals P out over P in. So, with P out, 1194, and P in as 1440, that's going to give us our efficiency. So 1194 divided by 1440, the result is 0.83. So you can express N as 0.83, or you can multiply 0.83 times 100% to give you 83%. Now, it says, what are the power losses? Well, remember, our P in value equals P out plus P losses. So if we want to know what P losses, we can simply take our P in value and subtract our P out value. So in this case, that's going to be 1440 minus 1194. Okay, and the result is 246 watts of P losses. Okay, so there's an example of efficiency and P losses and conversion from horsepower to watts, so that we can make a efficiency comparison and come up with a fraction or a percentage. Okay, so no doubt efficiency is always less than 100%. The closest thing we find in the electrical discipline anyways is a power transformer. So power transformers are able to be built to a 98% efficiency. Things like amplifiers, especially audio amplifiers and things like that, they have a very poor efficiency, and they're well below 50%. So whenever you have your audio amplifier on at home and really have the volume turned up, you shouldn't be surprised as to why there's so much heat that's being given off, and it's really because of how inefficient the amplifiers are. They're producing as much power in heat as they are output power as far as sound energy goes. So that's a lot of times a little bit of surprising fact for some people when they hear it. So what happens when we have one electrical system, or mechanical system even for that matter, where its power out becomes the P in value for another system, and then that P out becomes the P in value for a third system? Well, you'd have your initial P in value here. You'd have an efficiency for the first system, we'll call N1, efficiency for the second called N2, efficiency for the third N3, and then you'd have a final P out value. But how do you know calculate the total efficiency? Don't forget, it's a multiplication as shown here. A lot of times students want to add those all together, but if you were to add them all together, it's possible you could get a value greater than 1. And we know that's not possible. Nothing is ever 100% efficient. So that being the case, we multiply them all together. So N total equals efficiency of system 1 multiplied by efficiency of system 2, and so on. Right? And then that means that our P out value, would equal P out would equal P in multiplied by N total. Remember, N total would be a percentage or a fraction, so that'll just simply be a fraction multiplied by the total amount of P in that was going into the system, and this is going to give you the P out value. Okay, so that's it, guys. Next thing we'll do is do your practice questions from Robbins and Miller for Chapter 4, and then do the same thing if you have the Boylestad book, because it's Chapter 4 as well. So just go to D2L and look under the practice questions, and you'll see the assigned practices.